All right, so welcome everyone. So for today's talk, it's our pleasure to hear Gabriel Wong, who is a postdoc at Harvard, and he will tell us about interplay between edge modes, quantum computing, and Tqfts.
Thank you very much for the invitation to give the talk. I realized I should have put a title page that was matching with my abstract, but I didn't. I apologize for that, but my sort of title page is to tell you why I think edge modes and their surface symmetries are interesting, because they sit in this kind of intersection of three very vibrant areas, and they seem very different: string theory, quantum gravity, topological phases of matter, quantum information, and quantum computing. And in this talk, implicitly, we'll hit at least maybe this, this, and this. And so it might be too ambitious, but I hope that I'll give you an overview of what I've been doing. And please feel free to interrupt anytime. So I want to start by saying what edge modes are, starting with what I just will refer to as physical edge modes. Edge modes are degrees of freedom that we have to introduce to describe a system with boundary in a consistent way. For example, any anomalies in a gauge symmetry has to cancel between the bulk and the boundary. A very well-known example in condensed matter physics are symmetry-protected topological phases, or in fact, almost any gap topological phase like the quantum Hall system. When you have a boundary between a non-trivial and a trivial phase, there are always some usually gapless edge modes that have to be there in order for you to connect the two different phases. More generally, outside of topological matter, just in any gauge theory, including gravity, there are also edge mode degrees of freedom when we study either the theory in a causal diamond, or this could be the Penrose diagram from Minkowski space. So what we find is that when we study sort of Cauchy slice restricted to some subset V, at the corners here, there are some kind of edge mode degrees of freedom. When this picture is a picture of Minkowski space, these edge modes are the soft modes that have been studied famously by Strominger and many, many other people, which transform under the asymptotic symmetry group of the space-time. In this context, these symmetries are usually viewed as large gauge transformations. Another example where we think edge modes appear are at a black hole horizon. One sort of deep mystery about black holes is that from the outside, it looks like a quantum mechanical system with entropy that is proportional to the area of its event horizon. And this has led to something known as the holographic principle, which says that the gravitational degrees of freedom always, the gravitational degrees of freedom of a region of space-time is on its boundary. So a very vivid realization of that idea came from Marusena in the ADS CFT duality, where bulk quantum gravity in ADS, in D+1 dimension, can be described exactly by a dual CFT in one lower dimension. So the edge modes I described earlier, I would call physical edge modes. They reside at a physical boundary. But now I want to say something about entanglement edge modes, which live at an entangling surface. So one way to introduce them is to ask about how to define entanglement in a continuum theory, like quantum field theory, where the Hilbert space does not naturally factorize into subregions. So what I'm thinking of is in the Schrodinger picture, we have a wave function. Phi of x is a configuration of the quantum field on a constant time slice. It doesn't literally make sense to split up a time slice into region V and V bar, because well, the various subtleties having to do with what happens near the entangling surface. But the resolution turns out to be to treat V and V bar as independent systems with boundary, we call the entangling surface, and introduce edge modes just as if it were a physical boundary. These edge modes again will transform under a symmetry group that we'll call a surface symmetry group. The idea is that even though this entangling surface is not a real boundary, the fact that you are insisting on factorizing the Hilbert space will introduce a sort of fictitious boundary that will nevertheless probe the physical edge modes that would be there if it were a real boundary. So let me say more about this notion of edge modes because it's so central to this talk. So I'm going to discuss not any general QFT, but I'm going to talk about gauge theory. And in gauge theory, a basic idea is that the gauge invariant degrees of freedom are not point-like, they're non-local. Usually there's some Wilson loop kind of variables. So if I insist on partitioning a spatial slice between V and V bar, it always cuts some of these Wilson loops. So the physical Hilbert space of these loop variables does not factorize literally into a tensor product, but there's a well-known way to make this work, which is to extend the Hilbert space. So here, the region V has, and also V bar, has its own sort of stretched entangling surface. I've split this entangling surface into two with a small regulator. And when I do that, I introduce a boundary, and I have to allow these Wilson lines now to end on the boundary, ending on some kind of charges. This is what I need to introduce to give a gauge invariant description of each of these subregion Hilbert spaces. But these charges weren't there in the original picture. So this Hilbert space is bigger than the original one. Now, the way we're going to recover the original Hilbert space is that it's embedded inside a subspace. So one way to think about it, instead of thinking about this as embedding, we can think about starting with the larger Hilbert space and then co-shrinking by Gauss law. What this means intuitively is the Gauss law constraint will entangle these charges so that you recover a subspace of gauge invariant states that lived in the original Hilbert space. Once you do this, you can define what you mean by a reduced density matrix, and you can trace over this Hilbert space vector here. And then we can define the usual things like entropy, trace rho log rho. And one finds that in addition to some kind of bulk entanglement entropy, there's an edge term. And this comes entirely from these boundary edge modes. They're entangled, and they play an important role, for example, in topological entanglement entropy in topological phases of matter. Another reason these edge modes are important, aside from just defining entanglement entropy, is that they might realize the dream that gravitational entropy actually is counting states in subregions, so that it's equal to entanglement entropy. So to explain why you might even think this is possible, I want to go back to explaining how generalized gravitational entropy is defined in the Euclidean formalism. So there we study the gravity pattern in Euclidean signature, and we study a saddle point as a cigar geometry. And we want to compute this quantity. So this quantity is basically treating the Euclidean pattern as if it were a partition function. However, there's a very important difference between z of beta and a standard partition function. In order to get the area of a forward-generation term, we have to consider saddle points where the Euclidean circle is shrinking in the bulk. But geometry where the Euclidean circle is shrinking in the bulk is precisely a geometry where you would not say z is a partition function. Because in standard QFT, z of beta is a partition function if it's a pattern go on a space with a non-contractible cycle. So there's some tension here. In order to give a state counting interpretation of the entropy, we need the cycle not to shrink. But if the cycle didn't shrink, it would not give you the area term. So this gives you a puzzle. I mean, how can we make this definition that z is a trace? And if I plug, basically, morally speaking, if I plug in this back into the generalized entropy, I'll get trace rho log rho, which is what I'm looking for. So here's a very perhaps naive but important idea in interpreting this z of beta as a trace. We define what we call a shrinkable boundary condition, which I label by E. We simply remove the tip of the cigar and put back in a boundary condition that is the same as if I put the cigar back in there. If I succeed in defining this boundary condition, then the calculation of generalized entropy looks like entanglement entropy, because if I flatten this cigar, it looks like a disk with a hole in the middle. And it can treat this lower half of this annulus as a preparation of a factorized state between the region V bar and V. And then if I think about this annulus in the Euclidean time evolution, what it looks like is a reduced density matrix that's evolving V back into itself. So this gives an idea that you might think gravitational entropy is equal to entanglement entropy. And in fact, it has been proposed that the leading term in the gravitational entropy is exactly coming from the entanglement of the edge modes that reside here at the entangling surface. So I've already said maybe 3 different diverse situations where edge modes arise. And this talk is about a particular framework that sort of unifies all these different situations called extended Tqft, and in particular the type that was formulated by Moore and Siegel. The important new ingredient that Will Donnelly and I introduced is a notion of a shrinkable boundary condition, which we also call the entanglement ring. So in the past 2 years, we've applied this to a variety of situations: 2-dimensional Yang nodes, topological strings, 2D conformal field theory. And at the moment, we're working on similar applications to 2D gravity and 3D gravity. But actually, you might notice that immediately when I started listing these examples, I left the realm of Tqft. And so I should warn that I'm in some sense using this Tqft as an inspiration, but the particular examples that I apply to in many cases won't satisfy all the rules. But nevertheless, this sort of framework will still be useful as a guide. But I want to say that even though I know this is probably a quantum gravity crowd that I'm speaking to, the example that I want to explain in most detail is one that appears in this way of doing quantum computation invented by Rosendorff and Briegel, called measurement-based quantum computation. The reason I want to explain this is that edge modes are often described as things that transform under large gauge transformation. They appear as a lifting of gauge constraints at a boundary. That's correct, but as stated, it can be ambiguous in many ways. For example, a gauge symmetry is redundancy. And if I change duality frame, a gauge theory can turn into something that's not a gauge theory. So if I explain edge mode in terms of gauge symmetries, it is not duality invariant. And I'm sure many of you know, just classically, if you derive edge modes from a covariant phase space point of view, there are many ambiguities. But this recent work that I'm working on with these co-authors, we find edge modes appearing in an operational way when we try to perform quantum computation on an entangled state. And I like that idea because it gives some physical meaning to edge modes. They're not just formal for some theorists to write down a factorization, but they have some physical implications. Okay, so before I go on, are there any questions? This is just the introduction. Okay, so let me review what I mean by extended Tqft. So as I mentioned, there's an extended Hilbert space factorization where you map a physical Hilbert space into a larger one. That immediately begs the question whether this factorization is unique and whether there are constraints you should be putting on these edge modes and the surface symmetries. And the answer is yes, because if you didn't do that, then you could put arbitrary edge modes here and get arbitrarily large entanglement entropy between these two sides. So let's restrict to one dimension for now and try to address this question. We'll study theories usually that we think can be defined by path integral. Now, normally we think about computing scattering amplitudes of correlation functions. In this case, they would be on a Riemann surface, and we can break this Riemann surface up into basic components like a cap, a pair of pants, and a tube. And if I tell you how to assign a path integral, using the path integral, some quantity to each of these basic ingredients, I can glue them back together to get any Riemann surface I want. So that's one way that mathematicians would view the path integral. However, when we talk about factorization, we need to go beyond this kind of cutting. So here, I basically cut along circles. But now when I want to study factorization, I have to take a circle and cut the circle along a point. So that's cutting it here along a codimension 2 slice instead of codimension 1 slice. And similarly, I can cut an interval into 2 intervals, and etc. So what extended Tqft is some kind of categorical formulation of quantum field theory in terms of cobordisms, which are these little path integrals here, that will allow us to talk about this kind of high dimensional cutting. So let me start by reviewing what a closed Tqft is in 2 dimensions. So this refers to a category of cobordisms. The objects in this category are circles. The morphisms are these cobordisms, which are, you can think of evolutions between initial and final circles. And there are some sorting relations that tell us how these pieces glue together. There are some rules that make the gluing local. And a Tqft, a closed Tqft, we can view as just a rule that assigns Hilbert space to circles and linear maps to these cobordisms. When we see 2 circles that are disconnected, it becomes a tensor product. And when we look at an object like this, it's a linear map from 2 Hilbert space, tensor product Hilbert space to a single one. So it defines a multiplication. And this is just a state because it's a linear map from this C to a vector space. Now, the important thing about this rule is that the gluing, the composition of the linear maps have to satisfy the same rules as the gluing of the cobordisms. If we define things this way, then 2D Tqft is a Frobenius algebra with a pair of pants as the multiplication rule. As we alluded to earlier, we want to extend the closed Tqft to what I call the open sector, where we allow for intervals as well as the circles. Now, when I have an interval, I have 2 boundary endpoints, and I have to give some kind of boundary labels. We're going to think about these boundary labels as categories of boundary conditions. They're going to define the edge modes. In a very concrete way, these boundary labels will correspond to representations of the surface symmetry group. So for example, they can be, this Hilbert space HAB can be expressed in this form. Now, there's a sort of abstract way to think about this Hilbert space assigned to an interval that might seem weird, but is very relevant for us. Textbooks will tell you that an interval is a Hilbert space of states, but it should also be thought of a linear map between the boundary categories. So in other words, I can read this side to side as object, morphism, object. And what's interesting is that this kind of formal understanding of extended open sector of a Tqft actually has a physical meaning. In the more refined form of Tqft called equivariant Tqft, we'll identify this kind of linear map as quantum teleportation. Now, once I define intervals, I can fuse them together. And when I fuse them together, the rule is that the endpoints that meet and glue have to have matching labels. So one thing I should add to this notion of a category of boundary conditions is that it's a linear category. So what this means is that when I fuse together these 2 Hilbert spaces, these labels B, first they have to match, but also they could be a linear combination of other labels. And or when I say linear combination, I mean direct sum. And so when I fuse together 2 Hilbert spaces like this, it looks just like matrix multiplication. And so the shrinkable boundary condition that I referred to earlier will be a very special label, and it could be a direct, it is a direct sum in general of other labels, which we can think of as all the allowed representations of some symmetry group. So so when I put an E here, then I'm viewing this fusion as saying that this sort of endpoint here was really a stretched entangling surface. So I can fuse 2 intervals back into one because it was never really 2 different intervals. It was the same one that was factorized. Similarly, I can split an interval into 2 using this entanglement boundary condition. Now, all these boundary labels are not arbitrary. They have to satisfy sewing relations of the open sector. And it turns out that in the open sector, we get another algebra defined by this multiplication rule that doesn't have to be commutative. Okay, so finally, we have to study constraints that relate the open and closed sectors. So I should add maybe to this also these kinds of diagrams. So there is a set of constraints developed by Morsigo and these authors here. There's 5 of them. And it turns out that if you insist these boundary labels, or in particular this E label, satisfy all these constraints, then the cutting and gluing is consistent and local. So I don't think I'll say too much more about these. These are somewhat self-evident pictures if you think about them topologically, but if you translate them into the language of algebras, they also have some sort of meaning in terms of, for example, algebra homomorphism. So, for example, this zipper here is a map from the Hilbert space of a circle into an interval, but it has to be not any map. It has to be a homomorphism of algebras. So this first identity is saying that the identity element in the closed sector maps to the identity element in the open sector, which is something satisfied by algebra homomorphism. Okay, so what I said earlier was developed by Morsigo. The new ingredient we're going to add to the game is this notion of shrinkability. So if I take a circle and factorize it and I fuse it back together, I haven't done anything because, again, entangling surface is not real, it's fictitious. So that means that I should be able to split and fuse without making any, creating any change. So the entanglement brane axiom, which I call interchangeably the shrinkable boundary condition, just formalizes this idea. And it turns out in terms of the diagrams, drawing it this way makes it the most powerful sort of hole closing condition. It implies that all these, anytime you see E label around a hole, it always closes. So the annulus, for example, is equal to the sphere. So this picture here is the analog I drew earlier of like this cigar for the black hole, and saying that it's equal to the cigar with the tip removed. So the whole point of this extended Tqft is that we're going to use the rules as constraints so that the entanglement edge modes are going to be solutions of all these constraints. Okay, any questions so far? Okay, so let me say at least a few words about examples of this extended Tqft. So I'll start with 2D Yang-Mills or 2D BF theory. They're actually very closely related. So I can basically use the same formulas. So in 2D Yang-Mills or BF theory, a circle is assigned to class functions on a gauge group G. So class functions are spanned by the characters, the trace of holonomy U in some representation R. So I should just say more specifically, this U is the holonomy around the circle. If I extend to the interval, what I have now are just functions on G, so they don't have to be class functions. And these are spanned by the representation matrix elements, R, A, B, where A and B now are the edge modes. These are the new degrees of freedom that range from 1 to the dimension of the representation. Now, I'm just giving you sort of the answer for 2D Yang-Mills. What is the correct sort of extended Tqft formulation? So now in all these formulas, first thing one should notice is that this is not quite Tqft in the sense that this Hilbert space is infinite dimensional, right? The number of representations of a V group G in general is infinite dimensional. And therefore these should really have some Boltzmann factors to suppress so that you can have convergence series. So there should be really e to the minus area times Casimir. But I didn't include it because it's easy to put it in, and we can always take the A equals 0 limit to see the formulas. And the difference between BF theory and the difference between BF theory and 2D Yang-Mills will be that in 2D Yang-Mills, you put in the Boltzmann factor in area of the cobordism. In BF theory, you put in beta, which is going to be the length of the boundaries. Also, for example, the boundary of these annuli here. But otherwise, all the formulas for 2D Yang-Mills and 2D BF theory are the same. So as an example, if you look at this kind of fusion map of two intervals, what it really looks like is some sort of matrix multiplication, right? You see RAB, RBC, and then the indices here are summed over. And to make a long story short, you can check using these ingredients that the shrinkability is indeed satisfied, so that a sphere partition function, which is given by this, is really equal to a trace. The sum over one is saying that a sphere is really traced over an interval. The interval states are labeled by R, A, and B. And when you sum over them, you get these degeneracy factors in the partition function. Okay, so now I'll seemingly switch gears to talk about 2D JT gravity, which is with this GR coupled to a dilaton. But I'm not going to write down any Lagrangians. In fact, in this entire talk, there are no actions. I'm only going to talk about cobordisms. But let me say a little bit, at least what it is to 2D JT gravity is. So we'll be interested in the space-time that looks like this ADS2 wormhole geometry. So there are two sides here, and there's this wormhole that connects the two. Now, when we study the path integral for dilaton gravity, we could integrate out the dilaton first. And when we do that, we find that the action is entirely a boundary term. There's no bulk term. And so the degrees of freedom in this two-dimensional theory of gravity lives entirely on the boundary. And we can think of it as the degrees of freedom as parametrizing sort of a wiggly boundary here. So there's some cutout of this geometry. This cutout corresponds to when you impose what people call nearly ADS boundary conditions in the path integral. And each of these cutouts lives a Schwarzschild theory. Schwarzschild quantum mechanics. So I won't go into much detail about this other than to give you just the partition function for the Euclidean version of this Lorentzian spacetime. So the Euclidean version of ADS2 is just this disk here. And it has some boundary length beta. So from the boundary point of view, it looks like a thermal system. And I'm going to call the nearly ADS boundary condition just this, I'm going to give it a boundary label I. If I compute the path integral of JT gravity on this disk, what I get is this partition function. It has a Boltzmann factor and some kind of dimension factor that is, sorry, I'm missing an R, important R here. That will be crucial to our story. So it turns out that JT gravity can also be formulated as a BF gauge theory, except we have to be careful what the gauge group is. So formally speaking, we want to treat the gauge group as SL2R, but plus here meaning consists of the semi-group, which is to say that when I look at the matrices of SL2R, I only restrict to the case when all these matrix elements are positive. That sounds like a very strange thing to do, but what it really means is to say that when we study the representations that will be allowed in our categories, we only allow the principal series representations. And the reason this is important is that principal series representation precisely has the Planck measure given by R since 2 pi R, which is exactly what appears in the partition function on a disk. So we can talk about, again, the Hilbert space on an interval with some shrinkable boundary condition. And it turns out here, the shrinkable boundary condition E on interval gives you a Hilbert space that is a set of functions on SL2 plus. So again, what does it really mean? It means that the set of functions on this space is spanned by matrix elements in a particular set of representations. So R here has to be this principal series. If I allow other representations, what I would get is SL2 or universal cover of SL2. In this case, as opposed to Yang-Mills case, A and B are not discrete. They are continuous labels, and they label the eigenstates of the Cartan generator. I'm sorry, this J minus is not Cartan. This is J0, the Cartan generator of SL2. And then, so one reason I introduced JT gravity is here's a case where you have different, you really have to use different boundary labels. So when the boundary is when an interval approaches the asymptotic boundary, it has a boundary label I, which corresponds to restricting one of these A and B's to an eigenstate of one of the generators of SL2. So on this interval, Hilbert space, the only allowed wave functions of this form where this right index is fixed, but B is still allowed to be varied. So sorry, A is still allowed to be varied, but I is fixed. And we can play the same kind of game that with 2D animals. Here we can take this disk and we can ask, so what is the sort of Hartle-Hawking state you get by cutting the disk in half? So that would be this half of a disk here. And I've made the diameter kind of curly to indicate that because we're really talking about gravitational theory. So this is not a rigid kind of surface. And the state you get when you cut it in half is the Hartle-Hawking state, which depends on the length beta of the circle. It's given by this quantum state here, where these RIIs are just the matrix elements, as I mentioned earlier, of SL2 representation, except that both indices have been fixed to the asymptotic boundary label. So this is a purely group theoretical object. However, it also has an interpretation as the energy eigenstate of JT gravity. And in particular, if I write the group element U, which belongs to SL2 plus, in this Gauss form, then it turns out that by fixing the boundary labels to be I, the dependence on gamma plus 1 goes away, and it depends on phi, which corresponds to the geodesic length here along this slice. And again, we impose shrinkability with our choice of boundary conditions. And the shrinkability means that this disk partition function can be used as an annulus. And because this is true, we can use the argument I made in the introduction that when we compute the entanglement entropy, or sorry, the thermal entropy in this form, we can really, when we compute sort of this as a sort of gravitational entropy, we can really view Z of beta as a trace because it's an annulus. And we'll find that when we do this trace, we can do a saddle point approximation. And that saddle point approximation with the sinh measure gives us log of sinh 2 pi r for some special r, value of r, of special representation. And when we translate it back to the gravity variables, we get right on the nose the generalized entropy. So phi h here is the value of the dilaton at the horizon. So it plays a role of area in this theory. Okay, so are there any questions about what we've discussed so far? Okay, so let me move on. So I think I'm going to probably run low on time. But I still encourage everyone to ask questions because it's more important for everyone to follow than for me to finish. So now I want to change gears a bit and talk about something called equivariant Tqft with the purpose of eventually applying to study edge modes in measurement-based quantum computation. So I should say that one motivation for this is that when we look at applications to MBQC, we're going to look at lattice model, where it would seem like there's no issue of factorization, but it will still turn out that edge modes are important, and I think that gives you a good, maybe different point of view on edge modes that will be physically meaningful. So let me start with defining what an equivariant Tqft is. Start with the Tqft with some global G symmetry. And suppose we want to gauge the symmetry. In a path integral language, I will couple my Tqft to a gauge field. In the cobordism description, that means attaching a G bundle, a principal G bundle, to all the objects and morphisms. So now my circles have a bundle attached to it, so there's some G flux going through it. So there are twisted sectors labeled by group elements G. And the Hilbert space on a circle is the direct sum of the twisted sectors. This is something familiar, for example, in orbifold CFTs. My pair of pants now can be viewed as a multiplication that takes the twisted sector G1 and twisted sector G2 and mapped it to twisted sector G1 times G2. Again, now the kind of cap states that I described earlier are also now labeled by some kind of G twist. The new ingredient here is some kind of symmetry. And this symmetry is represented by simply inserting a holonomy or Wilson line variable here. So if I start with this circle here, and without the H here, it's just an identity map that maps one circle to another. But with the H here, what it does is it conjugates the twist element G to HG H inverse. And the new ingredient here is that when we couple a gauge field to Tqft, this pair of pants diagram is no longer commutative. The multiplication doesn't commute, but if you stare at this picture a while, topologically, it means that there's some kind of twisted commutativity. So phi1 and phi2, if they belong to the twisted sector labeled by G1 and G2, they don't exactly commute, but they commute if I apply alpha G2 to phi1 first, and then multiply phi2. And so there are other axioms here, but I didn't list them. And so it turns out this more refined notion of a Tqft gives you a Turayev algebra. This algebra refers to this algebra here of the states on the circle, and is classified by group cohomology.
Gabriel?
Yeah.
Oh, but so I'm missing kind of how this, I mean, this looks a lot like the usual definition of an extended Tqft, no? What is extra?
The extra thing is that I'm coupling it to a gauge field. So this sum over, for example, on a circle, we would not distinguish G and G, HGH inverse, right? In the Yang-Mills case, for example, like the circle corresponds to class functions. So these are invariant under conjugation.
Mm-hmm.
Here we're going to keep track of G and HGH inverse in the case that you have a non-abelian G. And also this multiplication is just not commutative, right? In the Yang-Mills case, if you remember, in Yang-Mills, there was a multiplication that is totally commutative. It was something like, it would be something like this. So this is a linear map that would take two circles into one circle. And of course, it doesn't, I mean, there's no ordering here.
Yeah, but that's the property of the category itself, right? Not of the fact that it's...
Well, that's right. This is a different category. So yeah, the point is that equivariant Tqft is a different category. So I mean, maybe I should say, yeah, it's a category with a bundle. So the category of cobordisms is different than the category of cobordism with the bundle. So for example, I put in these dotted lines so that I have to specify the holonomy along curves here to fully specify the cobordism. So basically coupling a gauge field to Tqft makes it not a Tqft in some sense. And the most obvious example here is if you look at this multiplication rule, it just can't be commutative, right? Because if G1 and G2 don't commute, you're in a completely different sector. If you multiply, right? So maybe I should draw it as a rule. If I draw it like this, if I do this exchange, so in Yang-Mills, this wouldn't do anything. The multiplication is commutative. But in this case, it's clearly not commutative, right? Because of this guy.
Yeah. But what I meant actually is, so like Turayev and the people you mentioned, I mean, they would call this a Tqft with defects, right? So it would still kind of fall within the kind of the framework of Tqfts, except that indeed you have more objects to keep track of, right? And the rules are different.
I'm happy to call it, yeah, I call it Tqft with symmetry, but you can call it Tqft with defect as well. Yeah, sure.
Okay.
Right. But it leads to a delicate classification that wouldn't be there for normal, right? Like this group cohomology classification is not there for this regular Yang-Mills. Any other questions? So I can see I'm way behind on time. So when should I stop?
So 15 minutes.
Okay. So let me try to budget appropriately. I might. Please still do stop me if things are not clear. So let me just say, what does it mean to have a group cohomology classification? Group cohomology classifies projective representations of a group. So for example, this means that when I take a representation matrix and I multiply them, it doesn't satisfy the representation property on the nodes. It satisfies it up to a phase B of G comma H. And group cohomologies classifies the consistent assignments of these phases. Now, we're going to take a very simple case in the story where our twisted sector has only one state. So it's a one-dimensional Hilbert space. So it's this state here with some G twist. And now the symmetry only acts by phases. So the phase is called discrete torsion. It's exactly the phase you get when you commute these two guys, and you get some epsilon here. And now multiplication is almost given by group multiplication, right? G1 and G2 multiplies to G1 times G2 here, but then there's again this projective phase. So that really is a new ingredient that distinguishes the equivariant Tqft. And now we can extend it, so we can take as our interval Hilbert space. Well, first of all, when we have an interval Hilbert space, we have to also define some notion of symmetry acting on the interval. And that's described by taking a strip and putting in some holonomy here. Now, it will not be a surprise to you that if the theory is classified by projective representations, the edge modes transforming projective representation. And we'll consider the simplest case, G is C2 times C2, where there's only one non-trivial projective representation given by basically the Pauli matrices. Now, the Hilbert space, which is labeled by these shrinkable boundary condition, has only one representation. That's the non-trivial projective representation. And these are the same wave functions that we saw in 2D Young nodes. So now, for example, I and J you can think of as spin up and spin down along some direction. And now notice that this shrinkable boundary condition is telling us once again that the Hilbert space on the interval is again a function space on a group. It's a space of function on C2 times C2, which is 4-dimensional. And in this simple example, the symmetry here just acts by either right or left multiplication. To notice a strange thing here, it's not strange, but it's maybe at first sight it seems novel. The labeling of states on the interval is given by the group elements G, but the labeling of the states on the circle is also labeled with group elements. That's just how things go, but there's nothing inconsistent about that. And now we can talk about, once we have the interval Hilbert space, we can factorize and fuse. So these are the same diagrams I drew before, except we have to be careful about these holonomies. And it's probably easiest to look at this definition here. We can see that really we're doing group multiplication up to a phase. These kind of definitions for the factorization and fusion are very nicely represented in the matrix product state notation. So as we said before, one principle of extended Tqft is every state G on the interval defines a linear map between the boundaries, which are edge mode Hilbert spaces. So given a wave function, I can write down an MPS tensor, which is of this form. And what this means is that when I project this index to G here, for each choice of quantum state G, I have a linear map from this left edge to the right edge, right? It's a tensor that sort of maps between the left to the right Hilbert space. This notation is useful because now when we fuse together two Hilbert spaces, all we're doing is contracting what will be called we're contracting these indices here up to the condition that G1 times G2 has to be G. And now we can do something that might seem just like a bit of a novelty. We can design sort of a qubit model of equivariant Tqft. What I mean by that is we start with a cap, and then in the identity sector, and then we open it up into open this state on a circle into state on the interval. But the state on the interval spanned by these matrix product states. And the fact that they came from the circle just means we got to tie together these indices here. So this is a trace of a representation matrix. And now, starting with this representation of our cap state, we can keep factorizing our state on the interval. And we use the entanglement boundary condition each time. In the matrix product state notation, I get a state that looks like this. What it is something that looks like a state in a very extended Hilbert space, right? Where I take in an interval Hilbert space and tensor it n times. And notice that even though there are many, many states in this Hilbert space, this trace is only, this wave function is only supported on the states here where the product of the G's are exactly 1, because trace, remember that these representation matrices are either 1, x, y, or z. And of course, only an identity element has non-trivial trace. So we're getting very close to what looks like a discretization of the circle into some kind of qubit model. In fact, we can make this very exact if I write the group element of Z2 times Z2 as a pair of binary numbers. Then these representation elements are just these Pauli matrices. And perhaps somebody in the audience will recognize that if I plug this back in here, this is actually the matrix product state description of the cluster state, which is a state that's used for quantum computation. So the punchline is that I turn a Tqft Hilbert space into an extended Hilbert space, and I want to think about this Hilbert space as a lattice of qubits. So 0 and 0,1 here are labeling spin up and spin down. Okay, in the last 10 minutes here, I want to explain what it means to have these projective edge modes and why I made this seemingly ad hoc idea of discretizing the circle by factorization. So the way I'm going to give meaning to these projective edge modes is to consider something called measurement-based quantum computation. So we don't assume any gauge theory of Tqft. We just start with an array of qubits on a lattice and ask how can we implement quantum computation only by measuring a quantum state. This seems impossible because the textbook definition of a computation, of quantum computation, is driven by unitary transformations, not measurements, right? Some unitary transformation acting on some logical qubits. So for example, here's like a standard quantum circuit. It's a C0 gate, right? It's two qubit gate that you use to do universal computation. So in 2001, Robert Rasendorf and Hans Briegel actually succeeded in proposing a scheme for quantum computation that's driven entirely by single qubit measurements. What makes this work is that the unitary map is hiding in some generalization of quantum teleportation. In this generalization, the teleported qubit is rotated by a unitary. And that's where this quantum circuit appears. The cartoon of this kind of computation is given here. You have an array of qubits, and you do some measurements. Here, the circles correspond to Z measurements, and a Z measurement disentangles these qubits from the rest, and it creates a logical structure. It creates a structure of quantum gates. So for example, this shape here, this kind of a junction here, is mapped to a C0 gate. And these arrows here are telling you exactly what direction you're measuring. Here, this arrow just means you're measuring along direction alpha. So for our purposes, we won't study this complicated two-dimensional case. We'll study 1D MBQC. And all you can do in 1D is simulate a single qubit unitary. But the novelty here will be that there's something called temporal order. When you do teleportation, you're measuring something, and the outcome is random. So you have to compensate for this if you want to simulate some unitary that you want. And it turns out, in a very clever way, MBQC achieves this by insisting that the future measurement angles, like the measurement angles for qubits you have not measured yet, depends on the outcomes of past qubit measurements. So this is what this picture is telling us. I measure these 4 qubits first on this line. And when I get to the ith qubit, which angle I measure depends on the past outcomes. And that creates a notion of time. That's what I mean by temporal order. So to understand how to design this state and why this temporal order appears, let's try to reverse engineer the state, which I'm going to call the 1D cluster state, by using the teleportation circuit as the basic building block. And this will directly connect to our Tqft story. So teleportation is a situation where Alice and Bob share an entangled state. So this is an entangling gate. There's a qubit that Alice has, and she makes a measurement of some kind of bell pair measurement on her shared quantum state with the qubit and herself. The bell pair measurement here, I've written it in a different way. There's some entangling gate here, but what this symbol means is I've measured along X in a single qubit way. So I measured one qubit along X, I got the outcome S1. I measured the second qubit along X, I got the outcome S2. And when Alice does this bell pair measurement, what happens is the qubit gets teleported to Bob, but it gets teleported, not exactly, it gets teleported up to a random byproduct operator. It's called a byproduct because you want it to really achieve the identity gates. But then this S1 and S2 are the outcomes, random outcomes, and it changes your state. And the way the protocol works is that Bob has to receive a message from Alice telling him what S1 and S2 is. The reason that he can now undo this byproduct is that the different outcomes are related by a Z2 times Z2 symmetry. In fact, this matrix here was exactly the matrix we saw earlier that gives us a projective representation of Z2 times Z2. And now I'm going to make the connection to this Tqft very precise by turning this kind of fluctuating circuit into a quantum state. So I take this circuit here, and I just draw some boxes around these gates, around these entangling gates. So then if I bend some wires around, I get this picture here. And what this picture is a matrix product state tensor, where these left and right indices are the indices where this qubit would be on. So every time if I fix S1 and S2, then this tensor defines a teleportation that maps the initial qubit to the out qubit up to this byproduct operator. But this is exactly the sort of matrix product state tensor that we found in extension of the equivariant Tqft with Z2 times Z2 symmetry. So now let me explain how sort of computation works on a 1D cluster state on a ring. So we saw that in the Tqft language, the extension of the identity cap state gave us this matrix product state. But basically what we found is that this matrix product state has an interpretation as a many body quantum state in which there is some kind of teleportation built into the system. So here, let me explain what that means. So the idea here is that these are physical qubits that correspond to the physical indices here. But because I've contracted all these edges of the tensor, the contracted edges are virtual qubits. So here's another picture. So I'm missing some legs here. So I start with my matrix product state. And every time I measure something, here I'm going to go from right to left. What I do is I perform a teleportation. Oh, I'm sorry. I'm not sure what happened. I just did something. Okay. Every time I measure a tensor here, I create a teleportation. So for example, I measured G2, and I teleported a virtual qubit from one virtual edge to the next edge. I measured G3, I do another teleportation. The teleportation is just application of these matrices. I noticed that even though each individual teleportation is random, this trace here, as we said before, it's only supported on states where the product of the G's gives you identity. That means that the total teleportation around this circuit here is always the identity gate. So I always end up teleporting the qubit without rotating it, because that was basically the holonomy of the state here in the Tqft language. And that holonomy is captured by the property of this wave function. Now, I could have done the same game in the Tqft with a twisted state. So I put some non-trivial holonomy along this sort of red edges. And now what happens is that the product of the G1s to Gn's have to give me not identity, but whatever this RH is. So this guy has to be RH in order for the trace not to vanish. And what this corresponds to is in this measurement-based quantum computation, I again do the same thing. I measure qubits one by one. And while the physical qubits are being measured, the virtual qubit is hopping, teleporting. But whatever it does in the intermediary stages, the total sort of circuit around the loop has to be R of H. So we simulated this quantum gate. So now I think I'm out of time, but if you just give me 5 more minutes, I'll just wrap up. So this idea that quantum teleportation corresponds to some holonomy was previously described by work of Susskind, Chuck, and Lampros. And the idea is that teleportation gives you an operational definition of parallel transport. So the final thing here is about simulating a general SU2 gate. So what's happening is that if I want something other than one of these 4 Pauli matrices, right? I had to superpose them with some arbitrary coefficient, and then I can get any SU2 I want. So we can implement a quantum state that will have this holonomy by just superposing the twisted states on a circle. And in matrix product form, they just look like this, where the wave function now has an insertion of U. So what we mean by computational output in the story is simply the following. We prepare a unitary, and then we just measure it, basically. What we're measuring here is these coefficients CH. But from this form of the wave function, CH just comes from taking the overlap of U with my twisted state. So this is the coefficient we're looking for, and we can explain this in Tqft diagrams. So this is my state U with some holonomy U, and this is just an overlap. But I do it in a maybe intermediary way. I first start with identity cap and I fuse it with U to create the U cap. And then when I measure, I take the overlap with the H cap. That's a trivial rewriting, right, of this overlap. However, it's physically meaningful because if I wanted to superpose 4 flux states with special coefficients, that's a hard thing to do in the lab. What MBQC does, this is not how MBQC is defined, but how we interpret it, is it takes a passive approach. I can also obtain this overlap in a different way. I just take this picture and I just bend this cap down like this. And now the holonomy is U dagger because the orientation is flipped. So what I can think of as the computational output C of H, instead of thinking about overlap of U and H, I can think of the overlap of the identity state, which is the cluster state, with this state, which is the fused product of the U dagger and H cap. So the miracle that happens here is that, so this is just a repeat of the figure from before. If I study what this fusion is of U dagger and H, it just means inserting this kind of Wilson line into the trace here. And what's interesting here is that if I carefully study what this state means, it means that I have defined new twisted sectors labeled by H, a new definition of holonomy that's related to the old one by a change of basis. It's a rotation of the different twist sectors. But if I study these twisted states in the extended Hilbert space, I see that the rotated sectors correspond to precisely the temporally ordered basis of MBQC. So I don't have enough time to explain in detail why that's true, but what I want to say is the following. The temporally ordered MBQ basis is very clever and not obvious that you have to adjust future measurements based on past outcomes, and that will compensate for randomness in the circuit. What we see in Tqft language is that translates into a very simple topological move where I just take this cap here and bend it down below. And so that's one of the novelties in the story. When we view MBQC in the Tqft language, it simplifies. So I'll conclude very quickly. I'll just say 2 things maybe. First, I want to emphasize this notion of shrinkability, which is really the most important Thawing condition. what it really tells you is what the correct edge mode symmetry is, including which representation of that symmetry should appear. And it seems to lead to the right answer for a state counting interpretation of black hole entropy. Now, I want to say a second thing, which is that in the MBQC story, why is there Tqft edge modes on a lattice? The answer is simply that edge modes characterize, or two things. Edge modes appear whenever we factorize in the presence of constraints. Constraints in gauge theory come from gauge constraints, but entanglement is also a constraint. So that's morally why we found edge modes on the lattice. If you impose some constraint, in this case having to do with SPT symmetry, again, you find edge modes due to those constraints. But what we find is something more, which is that the edge modes characterize the symmetry of the entanglement. And that symmetry, which when I say symmetry, I also mean the representation. That symmetry is actually useful for performing computation. And the particular representation of the symmetry is telling us the computational power of the state. So this might suggest, for example, I introduced this funny SL2R edge modes. What does it mean to have SL2R plus, sorry? It means I pick some special representations, but we don't have a really good physical meaning for why those representations give you the shrinkable boundary condition. But perhaps MBQC is telling us that we should think about the choice of representation as characterizing the entanglement of the quantum gravity vacuum. And so let me stop there because I'm out of time, and please ask any questions you like.
All right, thanks a lot, Gabriel, for this interesting talk. So are there questions? From the audience? Yeah, otherwise I'll go ahead. Yeah, so what is the, do you have actually a kind of a continuum, just field theory understanding of this I mean, maybe you mentioned this, but of this shrinkability boundary conditions? And because it seems that it's something that you need to include that is not here, neither in the Tqft story, nor, I mean, I understand in the JT story that, as you said, it's related to this choice of representations, but.
Oh, yes, so the shrinkable boundary condition is actually, when you say continuum QFT, I'm going to take a let's take JT as an example. But I'm not going to say it in the same way I said earlier in terms of representations. The idea is actually quite simple. I take a gravity 3 on a disk, and I insist that it equals gravity on an annulus, right? And the point is that in theories where there are gauge constraints, well, let me start by saying there's an obvious answer to this question of what this E is. I mean, I've removed the disk, right? So clearly what I should do is I just do the path integral on that little disk, and that defines a state on this boundary of this disk. And I put that state back in here, right, in this circle. So in other words, in the closed string channel, I know what the boundary condition is. If I think about the circle as where my Hilbert space lives, I know the correct boundary state is just a state on a disk. What is non-trivial is that I ask, what if I quantize on an interval? Then this direction is time. What is the boundary condition on the interval that will give me back the state defined by the disk? And the issue is that in general, in gravity theory, this boundary condition is non-local. One way to see this is because in gravity, I mean, well, this will sound like an on-shell condition, but actually it's true off-shell as well in JT. You're not allowed to have conical singularities in there. So the cone angle around this here has to be 2 pi. So there's some condition that the integral of the spin connection here is 2 pi. And this, by definition, is a non-local condition. It's like saying that holonomy around this circle here is not 1. And anytime you say the holonomy around a circle is not 1, then I can't put the, if I have a tau component of the gauge field along here, I can't fix it to a constant or anything like that, right? Because, for example, if I replicate the circle, it gets longer and longer, but the holonomy is always going to be 2 pi in order for it not to be a conical singularity. So what's happening here is that just purely in the terms of a continuum path integral, when I read the annulus in the open string channel, I have to, the shrinkable boundary condition becomes non-local. And one way to treat that is to say that, well, let me pause for a moment. I'm not going to, there's a solution that Jeffers gave and there's a solution that Mertens gave. But so is this clear so far? Like, so far, I haven't said anything about representations. I just said that you insist that the disk path integral equals the annulus path integral, okay? Yeah. That automatically implies what the boundary state here is. And for gravity, it automatically implies that the boundary condition here is non-local because you say we're not allowing conical singularities in the path integral.
Yeah, sure.
And then solution is very simple. You just, what's really happening is that if you take the JT gravity and you want to say it's equal to BF theory, it's not true. But it would be true if you put a defect here. The defect here, I'm going to call it D, means that it restricts to Chern class equals to 1. It fixes the measure on the BF gauge theory side. And of course, I can move this defect around. I can move it off to the side a bit, like this. And now, because of this equivalence, I can do the shrinkable boundary condition in BF theory. So this shrinkable boundary condition, for example, will be a tau equal to 0. And that is indeed the correct shrinkable boundary condition in BF theory. However, I've also accounted for the fact that BF theory is not equal to JT because I kept this defect operator here. And so the answer is sort of that in JT gravity, C of beta is not quite trace of e to the minus beta h. So this is the BF language. It's trace with a defect inserted. So this trace is taken over this Hilbert space of this integral here, where I put some defect operator. And this is actually going to be in some sense, a generic phenomenon. Like this condition is always true in gravity, and like in 3D gravity, we also expect this, and we also found a very similar thing like this defect in the topological string. And it comes from exactly like the same kind of thing. I mean, so here, this has to do with gravity constraints, which are non-local. In the topological string, the constraint is the Calabi-Yau condition that the strings move in some particular space-time. And really, it goes back to the idea of you're factorizing a Hilbert space in the presence of constraints. And when the constraints are very strong, then you can't get a local boundary condition. You have to kind of fix it somehow. And Jeffers and Koshmeier gave the solution, but the Mertens solution was different. He said, we don't have to insert a defect. We're going to use SL2R plus BF theory. And then there's no defect. Mm-hmm. But of course, you just push the non-locality. You push the non-locality elsewhere, because if you were to try to write down a path integral for this theory, it would also be non-local, right? Because there's no local condition you can put on the gauge field that will make all the holonomies live in here.
Yeah, sure.
Right. But the beauty of this extended Tqft story is I never had to write down a path integral. So that's also, maybe I'm not sure it was clear why applying to JT makes sense. If you insist on this formulation, then a path integral is very awkward. I actually don't know how to write it down. I've never seen anyone write that down. Any other questions?
Yeah, and the previous question I had was, I mean, I'm still not sure I understand the difference between the
Equivariant case.
the equivariant Tqft, because then you did an extension of the equivariant Tqft, and before I had understood that the equivariant Tqft was already like an extended Tqft. So
why do you call it? I guess I didn't understand that when I say extended, I mean defining it on intervals in addition to circles. But in this slide, I haven't defined anything on intervals yet.
But on this slide, you have defects, right? Because you have excitations. I mean, you allow for, as you say, you insert group elements and you insert holonomies in red.
Oh, I see. Maybe you're thinking, I think I know what you're saying. You're thinking, so I also maybe glossed over this. Or maybe it's not exactly what you're saying, but there's a point here, right? It's a pointed circle. So are you saying the circle in some sense is the interval? I mean, which is sort of true here, because the circle and the interval have the same Hilbert space in this case.
No, I'm saying there's extra data that you're putting on top of the Tqft because you're putting this red information, right? And
right, but that by itself is not called it. I mean, maybe it's a matter of name, but introducing a background gauge field doesn't have to do with extension. Like in the path formulation, I will start with an action as a function of some matter field, and then I add a gauge field A, which I don't integrate over. I just gauge it. I change the derivative to covariant derivative.
So in the field theory side, this is what this corresponds to. So it's just coupling to an arbitrary gauge field. That's what you're saying.
Exactly.
Okay. Yeah, because what I had in mind about an extended Tqft, in the sense that the Tqft in which you allow for defects, is that the defects, in a sense, they play the same role as this coupling to a gauge field, except that the defect structure is imposed by the structure of the underlying Tqft you start with. So it's not something that you can freely add on top, because the given Tqft you start with, once you make it open, has a certain defect structure that is imposed by, which is typically classified by this, these 2F algebras that you mentioned.
Actually, by the way, I should confess that I don't really know in detail what a derived algebra is, because I was following this work of Morse Siegel. They use a different language, but they just mentioned that this Hilbert space here is a derived algebra. So maybe I'm sure you're saying something equivalent, but in this language, they don't view the insertion of these operators as an extension. But as I say, there must be some relation, because you can see that where is this line operator inserted? It's inserted at a point on the circle. I mean, it cuts the circle, right? And yeah, the point is that these circles are always kind of cut in the sense that like there is a base point. Like if you gauge this theory, if you overflow this theory, if you were to integrate over gauge fields, if you were summing over bundles, in other words, if you did something like that, then what happens is that the G label will become a conjugacy class. So instead of a group labeling a circle, group element, it will be a conjugacy class. Mm-hmm. Because conjugation like this is just a gauge transformation, right? That's the usual thing. So and then as I said, this multiplication becomes commutative. Yeah. So there's a sense in which that when you orbifold, when you sum of gauge fields, you recover the circle without the point, in some sense. Like then you have this commutative multiplication, but you lose some information. You lose the non-commutativity of this guy. And somehow the measurement-based quantum computation makes sense with the fixed background field rather than summing over gauge fields. So, but I'm sort of with you in that, because we did this fixed background field thing, it looks like I would cut the circle in some sense. I think that's sort of why this multiplication here, right, is the same. Like this pair of Panth location here
Yeah, sure.
is just the same as this open pair of Panth location. And there are 4 states on the circles, there are 4 states on the interval. It's sort of like the interval is a circle. Yeah.
Okay.
And yeah, we can maybe later we can discuss a bit the 3. So we're trying to apply this in some sense to 3D gravity, and there we find something also again, the JT kind of story where it's actually even more, maybe better than JT. Here there's a Bekenstein-Hawking entropy that's equal to entanglement entropy, and there we find a similar thing, but with the QT form SO2 plus.
Oh yeah, you mentioned that, right?
Yeah, and it's sort of interesting that you can't get it from Trans-Simons. At least we don't know how to get it from Trans-Simons theory. There's some the shrinkable boundary condition in Trans-Simons theory has to be non-trivial. So I don't know how to get it. So instead we have this QT form version of Yang-Mills in some sense. And it seems to give the right area over 4. In that case, that's really an area. The right-hand side here is really an area as a function of the mass and spin of the black hole.
Mm-hmm.
I'm still very curious what the covariant phase space story is and how they.
But the quantum deformation you get in the what does the quantum deformation parameter come from? What is it related to? Is it also 1/, cosmological constant or something like this?
No, I have to think a little bit. There's a Q, I think it's something like pi I b squared.
Yes.
And this B is the B that appears in Liouville's theory. There's this background charge, and then this guy, I think, also appears. So I'm referring now to the Liouville. There's a Liouville-like CFT. Maybe I should call it Virasoro CFT. And the Q is a parameter in that CFT, sort of like the gravitational dual of the CFT. But now I'm not remembering exactly what. Let me look it up. You mean you want the relation to gravity, right?
Well, I just want to make your quantum group classical again, and usually you can take the deformation parameter to 1.
That becomes JT. The point is when you take Q to 1, you get back JT, which is SL2 plus. You do not get a classical limit in the usual sense of the quantum group. The classical limit is it's SL2 plus, basically. That's sort of the weird thing.
But I mean, you still, because I mean, usually at least in some versions of 3D gravity where quantum groups appear, the deformation parameter is related to the cosmological constant or to the Trans-Simons level. Or so that's why I was asking if here the Q that you have is also related to the cosmological constant. In which case, usually, if you send then 1/λ to infinity, then the quantum group becomes just a usual group.
It must be different in some way that I can't identify at the moment. I'm actually looking at my notes right now. Sorry.
In the meantime, I thank you again and stop the recording, maybe.
Oh, please do. I thought you had